Hello, everyone. Am I audible to all of you? Okay, so good afternoon to all of you. So today again, I am going to discuss the subsequent topic of process dynamics and control. So in the previous lecture, I was discussing about stability criteria and how we can understand the stability criteria. And that was with the help of Routh array. And we were forming the Routh array and we were observing the sign of the coefficient of the Routh array, right? That we have done this particular thing, and from there we were telling about that whether the system is stable or not. And it's one of the you know very frequent method to understand or to analyze the stability of a closed loop transfer function. The reason behind that is you only you have to only solve the closed loop transfer function and you'll get a polynomial in the S domain, and while observing the coefficient of the polynomial in the characteristics equation, if this is the characteristics equation here, so if all sign of all the character, I mean coefficient of the characteristics equation is positive, then the system will be maybe stable and may not be stable. But if any of the coefficient is negative, then the system will be certainly unstable. So that was the criteria that I have discussed in the previous lecture, and after that I have you know discussed with you how we can that a1, a2, a4, this a term will be given in the problem, and we can calculate this coefficient of in terms of a1, a2, or a3 in a domain, you can say, with the help of this characteristic equation. And after that, to make the Routh array, we have to calculate the value of v1, v2, v3, c1, c2, c3, e1, e2, f1, g1, and all, so and so forth. So we have calculated the value of b1, b2, c1, c2, e1, e2 with the help of this particular formula, right? So till now we have discussed we have studied all these things, and after that I was telling the element of the column first, that is a note a1, b1, c1 should be positive for the system to be stable. That already I discussed this array in the first column. If all the coefficient of the column first is positive, then the system will be certainly stable. And when if there is a sign change in the column first, if there is a sign change in column first, then the number of sign change will tell you the number of positive roots lies outside of the uh, you know in a complex plane. So again, this was very important. So here I have told you, here this 4 is minus, so here 7 is positive. Positive to negative one sign change, again negative to positive second sign change, and again positive to negative third sign change. So here you have observed that three sign changes are there. So if a system is if the characteristic equation is like that, something like that, and if three coefficient is negative, I mean if there are three sign changes are there, then these three roots of the characteristic equation will lie in the complex plane of right side. That's why the system will be unstable. I have discussed these things. And next thing I have discussed with you all, that all these particular things, if roots lies over here, then the system will be unstable. If roots lies here, system will be stable. If roots lies here, system will be stable. And if root lies here, system will be unstable. So if root lies in the third and fourth quadrant, sorry, second and third quadrant, definitely the system will be stable. And if roots lie in the first and fourth quadrant, then roots will be unstable. Now, one more thing I had discussed about that, that if root lie on the imaginary axis, let's say here, root can be here only. The real part of the complex number will be zero, then that root will lie on the imaginary axis only. So if root lie on the imaginary axis, then the system will be marginally stable. So you can write if roots lie on the imaginary axis, then the system will be marginally stable, right? So this was the case that I have discussed with you all. Now today, let's try to form the Routh array first, and after that we'll move forward to the some new problem today. So let's say there is a problem. Let's say let S4 plus this one is 3s square plus 3SQ, I think it should be 5s square plus 4s plus 2 is equals to 0. So now this one is your characteristics equation. So now how can I make the Routh array? So I have told you this will be a Routh array kind of thing. So in the first I'll be putting it. So you can write this in terms of this one. These characteristics equations can be written as, let's say, a naught s to the power 4 plus a1 s to the power. I mean, just try to follow one method. Let's say here I am writing a naught s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 kind of thing, right? So that's what the thing I am writing here. So a naught s to the power q plus a2 s square plus a1s plus a naught s to the power 0 is equals to 0. So now here there is a naught a2 and sorry, a naught a1 a2 a3. It should be a3 and it should be a4, right? So what I told you that I'll be writing here a naught a2 a4, right? Here I'll be writing a1 a3 a5, and if I will be writing b1 b2, here I'll be writing C1, C2. I can calculate B1 is equals to what? That A1, A2, A2 minus A naught, A3 divided by what? A1. Again, I can calculate B2, B2, that is A1, A4 minus A naught, A5. I'll be calculating A1, A4 minus A naught, A5, and again divided by A naught, A1. C1, C1 I can calculate B1, A3 minus A1, B3. So I can calculate, yeah, sorry, B1, A3 minus A1, B2 divided by B1, and I can calculate the value of C2, that is equals to B1 A5. If there is nothing, then it will be 0. I can write B1 A5 minus uh, B1 A5 minus A1 0, A1 into 0 divided by your B1. So this will 0, this will be 0, so that will be A5. Fine. So we have calculated the value of C1 and C2 all. So now, what is value of A naught? A naught is what here? 1. So I can substitute here 1. So I'll be removing all these things, and I'll be substituting the numeric value over here so that I can solve the problem. If anyone has any doubt, you can ask me, right? So your A naught is 1, A2 is what? 5, and your A4 is again 2. I hope these things is clear to all of you, right? And now your A1 is 3, your A3 is 1, or sorry, 4, this one is 0. Now this one is C1, so C1 is your B1 A3, right? B1, sorry, B1 we have to calculate. B1 is equals to A1, this one is A1 A2 minus, so 15 I can write here, that is your 3 into 5 minus 4 into 1 divided by your 3. So that is equals to 15 minus 4. That is 11 by 3. Now your B2 is A1, A4. So this one is your A1, A4, that is 6 minus A naught, A5. A naught, A5, that is 0 divided by A1. A1 is 3. So that is equals to 2. So we have calculated the value of B1 is 11 by 3, and this one is 2. I hope this thing is clear. Now, next is we have to calculate C1. C1 is B1 A3. So B1 A3, C1 is B1 A3 minus A1 B2. So that is 44 by 3 here. 44 by 3 minus A1 B2, that is 6 divided by B1. B1 is 11 by 3. So how much you will be getting? 18. If 44 minus 18, how much? 22 plus 2, 24. That is 24 divided by 3, right? And divided by 11 by 3. So this will get cancelled out. So it will be equals to your 24 divided by 11. And again, what is A5? So A5 is nothing, so 0. So now this one is your first row, right? Here you can see this one is your first row, and all the coefficient in this first row, that is a positive, right? So if all the coefficient in this first row is positive, then the system will be your stable. For second thing is that we would have understood that system is stable or unstable. Definitely, the system is if all the coefficient here is positive, then system may be stable, may not be stable, right? So if you understand if system is maybe stable, may not be stable, you have to make the root array, right? But if let's say if here be the if it is positive, if in place of positive, if the sign would be negative. So while observing this characteristic equation only, you can see the characteristic equation, and here there is sign that is negative sign, then system is unstable directly. But if it is positive, then the system may be stable, may not be stable. So we have to make the route array, and after that we can solve this particular thing, right? I hope this thing is clear to all of you. Anyone has any doubt? So this may be one kind of problem, and another kind of problem may be like that. So they can give you some this kind of row, that is 1, that is 11, that is 6, that is 6 into 1 plus Kc, 10 minus Kc, that is 0, and they'll give you 6 into 1 plus Kc. So they are telling you that I mean there is a character, there are a character. I mean uh, a closed loop response system is having a characteristics equation something, and from characteristics equation we have formed a route array, and we want to understand if the system is stable, then what will be the value of maximum value of Kc, so that system will be stable. So if this system has to be stable, what should we do? We can do that the coefficient of all the first row should be positive. This one is positive, okay. This one is positive, okay. This one has to be positive. So first, what will happen? 10 minus Kc should be greater than 0. So minus Kc should be greater than minus 10. So your Kc should be less than 10, right? So I have got this one. Now this coefficient has to be positive also. So can I write 6 into 1 plus Kc should be greater than 0. So 1 plus Kc should be greater than 0, and Kc should be greater than minus 1. So we have got Kc should be less than minus 10 and 10 here, and Kc should be less than minus 1. So the value of Kc here, let's say 10, here let's say 0, and here let's say minus 1. So the value of Kc should lies in between, then this particular system will be stable. So the maximum value, the Kc, the range of Kc will lie over here. So this range will give you the stability of the system. That if we are substituting any value of Kc in between minus 1 to 10, then this system will be stable. So sometimes they will ask you to calculate the range of Kc for which the closed loop response will be stable, right? So this is the way that we can solve this kind of problem. Anyone has any doubt? Hmm. I hope there is no doubt. Then I'll move forward to the some different kind of problem over here. So again, this one is very important kind of problem. Every year, get people used to ask some questions from here. So let's say SQ minus 3s square plus 11s minus 11. I don't know what they are writing. That is equals to 0. So we have to you have to tell whether the system is stable or not. Darshana, is this system stable?
It's unstable.
What stable?
Unstable.
This one is unstable. Why? Because here you see there is negative and there is negative. So two coefficients are negative. So system will be your unstable. But if it is positive, then what will happen? You have to make the route array. And once you make the right route array, and from there you can get all the coefficient, and you have to observe this coefficient over here. If any coefficient over here is negative, then definitely system will be unstable. And how many roots are there lies in the right side of the complex plane. So you can understand that number of sign change from here to here kind of thing. Is there any doubt? So if it is clear, then let's try to solve one problem, right? So this one is your Kc, right? This is a closed loop transfer function. And let's say this one is 1 upon s plus 1, right? So this one is your output product, sorry, output, and there is a feedback system over here, and the value of measuring instrument is 3 upon s plus 3. Fine. So again, it will come to the comparator. It will get compared. This is zeta. This is your x, let's say input. That is your set point. Okay, fine. So we have to understand whether the system is stable or not. For first, Kc is equals to, let's say, 9.5. Second, Kc is equals to 11. And when the value of Kc is 12, we have to understand whether the system is stable or not. So first, when we try to understand the stability of this particular system, we know we have to make the transfer function. So transfer function Gs, that is equals to C upon X. So I can write directly that Kc into 1 upon S plus 1 upon 1 plus Kc into 1 upon S plus 1 multiplied with 3 upon S plus 3. So now I told you that the denominator of the transfer function will becomes your characteristics equation. The characteristics equation is equals to 1 plus 3Kc divided by S plus 1 into S plus 3. So finally I can write S plus 1 into S plus 3 plus 3Kc, right, divided by S plus 1 into S plus 3. That will be equals to 0, characteristic equation. If you want to find characteristic equation, so can I write S plus, that is equals to S square plus 4S plus 3 plus 3Kc, that is equals to 0. So this one is your characteristic equation. Now, once we get the characteristic equation, the main aim is to make the Raoult array. So first try to see here, once you get the characteristic equation, here you see there is a positive, all the coefficients are positive. So directly we cannot say the stability and instability of the system now. If any of the coefficient would have been negative, then we could have told that, okay, this system may be, I mean, this system is unstable. But here all the coefficient is positive, so you'll have to make the Raoult array. So the system is your s square plus 4s plus 3 plus 3Kc is equals to 0. So how can I make the Raoult array? So I can tell s square plus 4s plus 3 plus 3Kc. This one is equals to 0, right? So now, I mean, either you can tell it directly, right? 3 plus 3Kc. Here the coefficient is 1, it is positive. Here the coefficient is 4, it is positive. So this coefficient should also have to be positive. Then the system may be stable. So you can directly calculate here 3 plus 3Kc should be greater than 0. 3Kc should be greater than minus 3. So Kc should be less than minus 1. Are you getting it? So the maximum value of Kc should be minus 1, then the system will be stable. Now, the thing is that you have calculated this particular thing, or you can calculate from this Raoult array. So you have to make Raoult array. So this is equals to A naught S square plus A1S plus A2 S to the power 0 is equals to 0. So here I will be substituting A naught, again A2, and here this one is A1. So the value of A naught over here is your 1. Value of A2 is equals to your 3 plus 3Kc, and the value of here, this one is your 4, right? So this will be 0. Now, if I want to calculate this value over here, so this one into this one minus this one divided by this one. So it will be equals to 3 plus 3Kc, and this will be 0. Fine. And here it is 0. So now, if we have to find the stability of the system, we have to understand that all the roots of the, I mean, all the sign here is positive. This one is positive, it's fine. This one is positive, it's fine. But here you see there is 3K plus 3Kc. Now the whether this particular thing is positive or negative, that depends upon the value of Kc. So I can write 3 plus 3Kc should be greater than 0. And similarly, I have got these things here from directly here, right? So that's what the case is. So 3Kc should be greater than minus 3. So Kc should be less than minus 1. So if the value of Kc is less than minus 1, here minus 1, minus 2, and 0. So for all the value of Kc which is less than minus 1, the system will be stable, right? So now we have asked that if Kc is 9.5, Kc is 11, and Kc is your 12, whether the system is stable or not. So for all the value of Kc here, that is given 9.5, 11, and 12, the system will be unstable because Kc should be less than -1 for the stability of this particular system, right? So this is, I mean, this is one of the way that they will be asking you the stability of the system, for a closed particular closed system. So I hope you people can solve this particular problem now. Anyone has any doubt? If there is no doubt, then you people solve one question from here. So one more question that I'm going to give you, that is S4 plus 6s cube plus 4s plus 1 plus k is equals to 0. Now find the value of k for which the system is stable. Just try to find out here. I'm giving you 2 minutes time. Just try to solve the other. Anyone has solved it? Again, this is very basic question. So, I mean, you can use two methods. Either you see here, this is positive, and that 1 plus k is there. So if all the coefficient over here is positive, if this system has to be stable, then what will happen? 1 plus k has to be positive, right? So either you can make a root array. So you can calculate a naught s4 plus a1 s square plus a1 s cube plus a2 s square plus a3 s plus a4 s to the power 0 is equals to 0. So in the Routh array, how can you find out a naught? A naught here is 1, a2 here is again 0, and a4 here is your 1 plus k. Is it clear? K is greater than -1. Okay, let's see. And next one is that uh, here A1 S cube. So your A1 is 6, and your A3 is 4. Again, this one is 0 over here. So once we want to find out the value over here, so this one is 6 into 0 minus 4 divided by 6. So minus that 2 by 3, and here it will be 6 into 1 plus kc by 6. So here it will be 1 plus kc. Now here, what will the value? Minus 2 by 3 into 4, that is minus 8 by 3 minus 8 by 3 minus 6 into 1 plus kc and divided by minus 2 by 3, and this will be again here it is 0, right? Anyone has any doubt? And what will be the value over here? That is this one minus multiplied with this one minus this one multiplied with this one divided by this one. So here the value will be getting 1 plus Kc. So now all the coefficient in the first column should be positive. So this one is positive, fine. This one is positive, fine. But here there is a negative. So definitely now you can see there is a one sign change, positive to negative, right? So one sign change is there. So if this is negative, then definitely system is unstable, right? Now, how can I calculate the value of K? So here you can see two things are there, right? So the thing is that you can say minus 8 by 3 minus 6 into 1 plus Kc divided by minus 2 by 3 should be greater than 0. So can I write minus 8 by 3 minus 6 into 1 plus Kc, right? So should be greater than 0, right? If I'll multiply this side. And if I'll multiply negative sign both sides, so 8 by 3 plus 6 into 1 plus Kc should be less than 0. 6 into 1 plus Kc should be less than minus 8 by 3. So 1 plus Kc should be less than minus 2, 4. So minus 4 by 9. So 1 plus, sorry, Kc should be less than minus 13 by 9. So here we are getting Kc should be less than minus 13 by 9 1. And here Kc should be less than minus 1 from this one. Sorry, Kc should be greater than minus 1. Kc should be greater than minus 1, right? So the system will be stable. So Kc should be greater than minus 1. So now here two things are there, right? One is Kc should be less than minus 13 by 9 and Kc should be greater than minus 1. So either Kc minus 13 by 9 minus 1 point something. So here this one is minus 1, this one is minus 1 point something. Let's say minus 13 by 9, right? So either Kc should be less than minus 13 by 9 or Kc should be greater than minus 1. For all these value, the system will be stable. Otherwise, the system will be unstable, right? So again, this type of question is very, very important. GATE will give you this kind of question only. Again, I am telling you, these types of two intersection, two union kind of questions for the value of Kc. So all these values, so if the system has to be stable, then the value of Kc should be greater than Kc should be less than minus 13 by 9 or Kc should be greater than minus 1. These two value will be there for which the system may be, I mean, that will show the stability for the system. Anyone has any doubt? Okay, so this was the criteria for the Routh array from which we can understand whether the system is stable or not, and we can understand this particular thing. So I'm giving you one problem for the homework so that you can do these questions at your home and you can let me know whether the system is stable or not and how. So yeah, so this is a closed loop transfer function, closed loop response, that is the K, that is 1 upon 1 plus SQ, 1 upon 1 plus S whole cube, fine. This one is something like that, fine. And again, this one is a feedback over here, 1 upon S plus 1, fine. And yeah, this one. And fine. So again, this one is your input, this one is positive, this one is your negative, fine. And this one is your R. Let's say R is your input, C is your output, fine. And this one is a closed loop transfer response. And you have to tell that first determine the value of Kc above which the system is system is unstable, right? So yeah, this one is your homework that you have to do this question at your home. And till now, this was very important topic for the GATE examination point of view, because every year you will see 2 marks question will be there from this particular topic, right? So I hope I have, you know, solve lots of question in the class, as well as I've given you some kind of these kind of question has been given in the test series also. So once you will solve the problem in the test series, definitely you'll get some good idea about the solving of this root Routh criteria for the stability of the closed loop transfer function. Again, I'm telling you, Routh criteria is only applicable for the stability of closed loop transfer function, right? It's not telling anything about the open loop transfer function, right? So that is the thing that you have to keep in your mind first. Second thing is that Raoult criteria only tells you whether the system is stable or not, right? All these things I have discussed in the previous lecture, but how much stability, how much system is, tending towards the stability, or how much system is deviating from the stability. This has not been, told by Raoult, right? So to understand these things, whether the how system is deviating from the stability, we have to study some different kind of method that we are going to study today, that is the frequency response. But Routh criteria only tells you whether the system is stable or not. First, second thing is that Routh criteria is not applicable for the time delay system, right? Whether there is transportation lag in the system. I'll discuss the transfer function of transportation lag today also. But again, only this is applicable for the system having a characteristic equation in the form of the polynomial function, right? If characteristic equation contains, or if the transfer function contains the transportation lag or time delay, then the system, I mean, you cannot apply the Routh criteria for the stability of the particular system, right? So this is one of the drawbacks of the two drawbacks of your Routh criteria. And to overcome these drawbacks, we will be studying the frequency response today, right? Again, frequency response is very important topic. Every year in GATE examination, 2 marks question used to come from the frequency response, right? So let's start frequency response. So till now, I have told you, if I am talking about input, right? So I have told you different kind of input, that is your step input, impulse input, that is your ramp input, and fourth input I told you when I was starting the lecture of process dynamics control, that is sinusoidal input. So I have discussed all these things, that step input, ramp input, and sinusoidal, these three input systems in your top part first. But in frequency response, I'll be talking about the sinusoidal input, right? So frequency response of the transfer function, or whenever we talk about the frequency response, why we call it as frequency response? Because the input is our the sinusoidal input. That's why this particular topic is called as the frequency response. And what is this input? This input is called as the forcing function, right? This input is called as the forcing function. Why it is forcing function? The reason behind that is, if you will change the input over here, right? If you will be sleeping continuously throughout the 24 hour, you are not going to crack the GATE examination. But if you will be studying 18 hours every day, then definitely you are getting under rank, right? With effective, study. So your input is this one, how much hour you are studying. That is forcing you to study much more and more to crack the GATE examination. But if you are sitting idle at your home, if you will be sleeping only, then definitely you are not going to crack the examination, right? So that is what the input works over there. So again, the system in process dynamics and control and in S3 works also, that will require some kind of forcing functions to, show some output, right? Just like your input is a study, your output is getting some good result in GATE examination. So the same thing that will happen with the process dynamics and control also, that forcing function will be the input and output that we want to analyze, whether this is temperature change, whether this is a concentration change, whether this is your change in the height in the particular tank, change in height of the liquid in a particular tank, right? So all these things are the output, right? So in this particular topic, we are going to study about the frequency response, and the frequency response will utilize the step input, sinusoidal input, and we'll see how this particular input affect our system. Again, in this particular topic also, we will be studying about the sinusoidal input for the first order system, sinusoidal input for the second order system. Again, we will be talking about all these criteria, that controller that we have studied previously, that I mean, P controller, PI controller, PID controller, how the sinusoidal input will be changing the output of the particular system, right? So let's try to understand how we can understand the dynamics of this particular system. So to understand this frequency response for the sinusoidal input, we have to understand some basics of the complex number. I hope you must be knowing all these things. Basics of the complex number. So whenever we talk about the complex number Z will this will be denoted by Z, and Z is equals to A plus IB, right? Where A is called as the real part of the complex number, real part, and your B is called as the imaginary part of the complex number, imaginary part, and this small I is called as the iota. That shows the imaginary part. So the imaginary part of the complex number will be multiplied with the iota, right? So whenever we want to calculate the magnitude or amplitude of a complex number, amplitude, so that will be equals to modulus of z, that is called as modulus, that is equals to root over a square plus b square, right? And in complex number, we study the angle theta or the angle phi, that is equals to tan inverse, that is b divided by a, right? All these things I have discussed. What is b by a? Then if you talk about a particular number in complex plane, so in this complex plane looks like this one. Here, this one is your real axis. This one looks like your imaginary axis. So a number, complex number, that is z, that will be denoted by z, that is a plus ib, right? So I want to calculate this angle phi. So this angle phi will be equals to, this value will be your a, and this value will be your b. So this tan phi, that is equals to b divided by a. So phi we can calculate, that is tan inverse b by a. So this is very basic things. You have studied all these things in class 11 or 12, that I'm not going to discuss. But this is the essence of the complex number that I wanted to discuss with you, right? Now, I'm coming to the transfer function over here. I mean, nothing more we have to know in this complex number particular thing. This is basic. If you are knowing these things, then it's much more sufficient, right? Now, one more thing is that, let's say two complex numbers Z1 and Z2 are there, right? So let's say Z1 is equals to A plus IB, A1 plus IB1, and your Z2 is equals to A2 plus IB2, right? So if I want to calculate mod of Z, that is equals to mod of Z1 plus mod of Z2, right? If Z is equals to Z1 plus Z2, then I can calculate mod of Z is equals to mod of Z1 plus mod of Z2, right? And let's say Z is equals to your A plus IB. So can I write A plus IB, mod of A plus IB over here, mod of A plus IB, that is equals to mod of A1 plus IB1 plus mod of A2 plus IB2. This is basic. I should not discuss these things, but let's try to, recapitulate these things in your mind so that the thing will be very easy for you. That's why I'm discussing all these things over here, right? So if I'll calculate this thing, so this will be equals to a square plus b square, that is equals to mod of a square plus b square here, plus root over, sorry, a1 square plus b1 square plus a2 square plus b2 square, right? So this is the thing, that if you are adding two complex number, then modulus will be looking like that, right? So if I want to calculate phi is equals to phi1 plus phi2, right? So phi is equals to, here you can write tan inverse b1 divided by a1 plus tan inverse b2 divided by a2, right? So this will be your phi of complex number. If you are adding two complex number, that is z1 and z2, then the phi will be equals to tan inverse b1 by a1, here b1 a1, and tan inverse b2 by a2, here that is b2 and a2. So this is some basic stuff regarding the complex number, right? So I hope it is clear to all of you now. This is just a basic thing. Now I'll move forward towards the transfer function. So first I'll be talking about, let's say your axis. Axis is equals to a sine omega t. Sorry, this one is x3, right? This one is your x3. This one is your input. And which input is there? That is sinusoidal input. So now we will be playing with the sinusoidal input, right? So that is very important. Now I'll be talking about the transfer function, right? So the transfer function of your, let's say, first order process. So since if it is your xt, that is equals to your a sine omega t. So what can I write? Xs is equals to what? A omega upon what? S square plus omega square. I'll take the Laplace transform of xt and I'll get xs domain, t domain into s domain. So this one is your input, right? In s domain. And this one is your input in t domain, right? So now let's say your transfer function gs. gs is equals to ys upon xs, right? That is equals to, let's say, 1 upon tau s plus 1, right? This one is your, let's say, first order transfer function, right? So let's say Kp by tau s plus 1. I am assuming here Kp is equals to 1. So can I write that Ys divided by Xs, that is equals to 1 upon tau s plus 1. To make calculation easy, that's why I'm making using Kp is equals to 1. Fine. So here we are trying to give a sinusoidal input over here, Xs. So Xs is equals to A omega upon S square plus omega square, right? So I'll be giving you the input, that is A omega upon S square plus omega square multiplied with what? 1 upon tau s plus 1. So I want to convert that ys into your yt, right? So I'll take Laplace. So I can write Laplace of ys, that is equals to here Laplace of a omega divided by s square plus omega square multiplied with 1 upon tau s plus 1. Fine. So this is the Laplace. But you see, one thing is that you don't have to remember all these Laplace and all kind of thing. Again, this is very complicated. You have to do the partial fraction and all. So it's better, I'll recommend you to write directly remember this. Or if you don't remember this, then no one is going to ask you the Laplace of this particular thing. But the output should be very important. You have to understand what is the output. So I'm directly writing here, that is your yt, that is equals to a omega tau e to the power minus t by tau divided by tau square omega square plus 1 minus a omega tau divided by tau square plus omega square, fine, that is cos omega t plus a upon tau square omega square plus 1 sine omega t. So this one is very, very big kind of equations you will see. That is the Laplace of first order system. That is the output of the first order system in, with respect to the sinusoidal input in time domain. That is a omega tau to the power minus t by tau, tau square omega t, tau plus 1 plus this kind of thing, right? So you will see this kind of trigonometric kind of thing will be there, right? So again, if I more simplified it, so if I want to simplify it more and using that trigonometric function, so I can write this one is a omega tau upon, that is your tau square omega square plus 1 e to the power minus t by tau plus a upon root over 1 plus tau square omega square sine omega tau plus 5. Right. So ultimately, this you can simplify that equations that has been written earlier, and this will be looking like that, right? So here you see this one is a function of time. This one is also a function of time. Here you will see there is sine omega t plus phi, right? There is sine omega t plus phi. So I can write that phi is equals to directly tan inverse minus tau omega. Phi is equals to tan inverse minus tau omega. So at t tending to infinity, I want to find out why t tending to infinity, right? So that is equals to what? A omega tau upon tau square omega plus 1 into e to the power minus infinity plus a upon 1 plus tau square omega square root over into sine omega t plus phi. So if I substituting t is equals to infinity, definitely this value will be lies in between minus 1 to 1, right? This is not going to be infinity, right? Fine. Oh, sorry. So this is not going to make it infinity. So, but this particular things will be 0. So y at t tending to infinity, that will be equals to a upon root over 1 plus tau square omega square into sine omega t plus phi. Sine omega t plus phi. Is it clear? So this one is your output at t tending to infinity, right? This one is your output at t tending to infinity. That is your output steady state value. That means output steady state value, right? So the value of phi already you can calculate, that is phi is equals to tan inverse minus tau omega, right? Tan inverse minus tau omega. Tau is the time constant of the first order transfer function. Omega is your frequency over here, right? So now you can see you have given xt is equals to a sine omega t, and you are getting your yt that is equals to a upon root over tau square omega square plus 1 into sine omega t plus phi. I'm writing here, don't worry. So our input xt that is equals to, we have given a sine omega t right here in this transfer function, where transfer function is 1 upon tau s plus 1, and we are getting yt that is output that is equals to a upon tau square omega square plus 1 root over sine omega t plus phi. I think this one is root over, right? Yeah. So this one is your input, this one is your output. So input is omega t, right? So let's say if I want to draw the profile of this particular input, right? Let's say this one is your t and this one is your x and yt, xt and yt. So sinusoidal input is this one, a sine omega t, right? Here a is called as the amplitude of the sinusoidal wave, right? So let's say this amplitude of a is like that. So sine function will work sine. So this one is your a and this one will be your minus a. So sine function looks like this one. It goes like that. Sorry, there is no attenuation over here. I can draw some better profile over here so that you can understand. So sinusoidal function goes like that. And this one is your xt, right? This one is your xt. This one will be 0. This one is pi, 2 pi, 3 pi, 4 pi, 5 pi, and something like that. But now just tell me one thing. This one is your output. So since tau is positive, omega is positive, 1 is positive. So all this denominator is positive. And I am dividing a by denominator. So the overall amplitude will get decreased. So definitely this will go like something in this way. Let's say I am doing this one. So your output amplitude will be less than compared to the your input amplitude. This will be like that only. Blue one is your output, right? So this value is a upon root over tau square omega square plus 1. Again, this value is minus a upon root over tau square omega square plus 1. And now sinusoidal value is sine omega t plus phi. If phi is 0, then it is sine omega t. But if phi is negative, right? If phi is negative, then this will not start from here. Are you getting it? If phi is negative, then this is not going to start from here. So this is going to start somewhere later on. So this will be your output. This will go here. Again, this will come here. This will go here. Again, this will come here because this is your maximum amplitude of this particular thing. And your output will be looking like this one, something like that. So your blue one is your output. This one is your YT and this red one is your X3. So the you can see that amplitude of the output is getting decreased. So there is a attenuation over here, right? You can see there is a attenuation in your output. So your signal will get attenuated. your signal will get attenuated for the output. Means, since the magnitude of input over here you are getting A, but you are not getting your A exactly. You are getting something lesser than A. So what is attenuation? The value is getting decreased. That's why whenever we are giving a sinusoidal input to a first order system, your uh, system will get attenuated. Your output signal will get attenuated over here, right? I hope this thing is clear. First thing. Second thing is that here there is a value phi. So phi I have told you that is tan inverse minus tau omega. Tau is positive, omega is positive, but there is negative. So this will be your negative. So your phi will be equals to negative. So if phi is negative, then the system output will lag with respect to input, right? If phi is negative, then your output, what we say is your YT will lag with the input with an angle phi, right? With an angle phi. So here you can see your output is lagging with your input with this particular angle, right? Anyone has any doubt? Do you have any doubt? If you have any doubt, please ask me right now. Otherwise, I'll move forward. So again, I'm telling you, this is the case of when we try to give a step input for the first order system, and the system will behave like that, right? So one more method that is very easy method to understand this particular thing is that in frequency response, right? So what we do in frequency response, just try to understand. In frequency response, what we do, your GS that is equals to what? Let's say 1 upon tau s plus 1. This is your first order system. This is your first order system, right? So I will substitute S is equals to j omega. So this will be G of j omega that is equals to 1 upon tau j omega plus 1. So now this is in terms of complex number, right? So what I'll do that I'll do G of j omega that is equal to 1 upon 1 plus tau omega that is j, and I'll multiply 1 minus tau omega into j in numerator and denominator. 1 minus tau omega into j. Fine. So I can write 1 minus tau omega into j divided by 1 plus tau square omega square. Is it clear? So again, I'll separate real and imaginary part. So I can write 1 upon 1 plus tau square omega square, fine, minus tau omega divided by 1 plus tau square omega square, fine, and this one is your j. So this one is a plus minus ib. This is in the form of a plus minus ib, right? So if I want to find out magnitude of g of j omega, if I want to find out magnitude of g of j omega, so I can calculate magnitude of 1 upon 1 plus tau square omega square minus j here, and that is tau omega upon 1 plus tau square omega square. This is a complex number, so if I want to find out the magnitude, this one is your a and this one is your b. So the magnitude will be equals to what? A square plus b square, right? So I can write 1 upon 1 plus tau square omega square plus 1, that is whole square, plus what? Tau omega by 1 plus tau square omega square whole square. Is it clear? So finally, I'll be getting 1 plus tau square omega square divided by 1 plus tau square omega square whole square. So this will get cancel out. So we will be getting 1 upon root over 1 plus tau square omega square, right? So this, the magnitude of g of j omega, that is equals to 1 upon root over 1 plus tau square omega square, right? And this is for the first order system. And this one is called the amplitude ratio. This value is called as the amplitude ratio, that is ratio g of j omega, that is for first order system, that is root over 1 upon 1 plus tau square omega square, right? If this is a first order system, we can calculate the amplitude ratio of the first order process. Now, once we have calculated the amplitude ratio, we can find out the value of phi. So previously I have discussed that if z is equals to a plus ib, then phi is equals to what? Tan inverse b by a. So here g of j omega, that is your complex number, that is in the form of 1 upon 1 plus tau square omega square minus j into tau omega upon 1 plus tau square omega square. So here this particular value will show your a, and this particular value will show b, but here b is in negative. So can I write phi is equals to that tan inverse, right? The tan inverse minus tau omega divided by 1 plus tau square omega square and divided by 1 upon b by a. So 1 upon 1 plus tau square omega square. Again, this will get cancelled out. So finally, you will be getting tan inverse minus tau omega. So the value of phi here we have got, that is tan inverse minus tau omega, right? And this is your phase angle. And this tau omega is called as the phase angle for the first order system, right? So again, in frequency response here also, we have got the same phi value. And how this is coming, now you can understand these things by this way, right? Here we have got phi is equal to tan inverse minus tau omega, and here again we are getting phi is equal to tan inverse minus tau omega. So this is the way that we use to calculate the value of phase angle in frequency response with the help of the properties of the complex number, right? So this is very important property that you need to understand if there is first order system, and whenever we talk about the frequency response will be derived by the forcing function of sinusoidal function. And once we do give the sinusoidal input to a first order system, then we used to get this is the amplitude ratio 1 upon 1 plus tau square omega square and the phase angle phi, that is phi tan inverse minus tau omega. Any doubt? Okay, so if you don't have any doubt, then let's say we are having a transfer function, let's say gs, that is equals to 1 upon 0 point s plus 1. Fine. And let's say omega is equals to 10, then calculate amplitude ratio and phi. Calculate amplitude ratio and phi for this particular system. So calculate within 1 minute. Fast. Oh, have you calculated? This is very simple. You should calculate these things, right? Right now, for first order system, I told you first order system amplitude is equals to root over 1 upon 1 plus tau square omega square. Omega is given 10, and what is the value of tau? Tau is 1. So can I calculate the amplitude ratio, that is 1 upon root over 1 plus tau is 0.1, omega is 10. Calculate, that is equals to 1 upon 1 plus 1, right? So 1 upon root 2, that is 0.707. Fine. Now I want to calculate phi. So can I calculate phi is equals to tau 10 inverse minus tau omega. So that is 10 inverse minus tau. Tau is your 0.1. Omega is your 10. So can I write 10 inverse minus 1, that is equals to minus pi by 4. Is it clear? Anyone any doubt? Do you have any doubt? Please ask. Darshana, any doubt?
No, sir.
Okay. So this was your first order system, right? Whenever we talk about the first order system, we can say, no, let's say if I want to calculate in terms of Kp is also there, right? Let's say this one is Kp. So how can I calculate the amplitude ratio and phi? So first you have to do G of S is equals to J omega. So I will be substituting S is equals to J omega, tau into J omega plus 1. After substitution, I will rationalize these things, right? So G of J omega, that is equals to Kp divided by 1 plus J tau omega into 1 minus J tau omega divided by 1 minus J tau omega. This is just a rationalization thing. That is Kp minus tau omega Kp into J divided by 1 plus tau square omega square. Fine. So again, I'll separate the real and imaginary part. That is Kp divided by 1 plus tau square omega square minus J, and that is Kp tau omega divided by 1 plus tau square omega square. Simply, if I want to find out G of J omega, modulus of G of J omega, that is called as the amplitude ratio, and that will be equals to, this one is your A and this one is your B. So I will be writing Kp upon 1 plus tau square omega square whole square plus Kp tau omega divided by 1 plus tau square omega square whole square. So here you will see 1 plus tau square omega square and plus tau square omega square, it will come out of the integral root. So that is 1 plus tau square omega square. And here you will see that is Kp square plus tau square omega square kp square. So again, kp square will come outside. So this will be kp into 1 plus tau square omega square root over divided by 1 plus tau square omega square. So that is equals to kp divided by root over 1 plus tau square omega square. So there kp was 1. So this was 1 upon 1 plus tau square omega square in this particular function. 1 upon 1 plus tau square omega square. But if kp is there, then here you have to just substitute the value of kp, right? So this is the simplest way that you can understand this particular problem. And and again, I have told you this is the basic method that you can calculate the amplitude ratio and value of phi. First, you see the transfer function. After that, substitute s is equals to j omega. I'll substituting here. We'll rationalize these things. You know this particular mathematics. And after the rationalization, you can calculate the value of this amplitude ratio, that is root over a square plus b square, and the value of phi, that is phi is equals to tan inverse b by a. So this one is your b, this one is your a. So this one by this one, so that will be equals to again minus tau omega. Right. So again, here you see the value of phi does not depends upon the value of kp, right? This is independent of the kp. So this one is your first order function, transfer function, when we are giving a sinusoidal input in terms of frequency response, right? So we can calculate the value of amplitude ratio and phase angle. So basically, if I want to tell you what is the amplitude ratio, so amplitude ratio is modulus of g of j omega. And what is value of phi? Phi is angle that is equals to of g of j omega. Now, if I want to talk about first second order process. So what is your second order process? So can I write GS is equals to, let's say, Kp upon tau s square plus 2 zeta tau s plus 1. So this one is your second order process. And we are very much interested in knowing the value of amplitude ratio and phi. So how can I calculate? I'll substitute s is equals to j omega. So g of j omega, that is equals to again kp upon tau s square j omega whole square plus 2 tau zeta into s is equals to j omega plus 1. So can I write here that is kp divided by minus tau square omega square plus 2 zeta tau tau omega j. Again, this one is just a simple mathematics plus 1. So again, I'll have to rationalize these things to separate this. So 1 minus tau square omega square plus this one is j. So 2 zeta tau omega. So once I'll rationalize this, how? So 1 minus tau square omega square minus j into 2 zeta tau omega and divided by 1 minus tau square omega square minus j into 2 zeta tau omega. This is just a rationalization process that we generally do in the mathematics, right? So finally, you will be getting kp into 1 minus tau square omega square minus 2 zeta tau omega j and divided by that is 1 minus tau square omega square minus 2 zeta tau omega whole square, and that is your plus. So this is your real part, real, and this one is your imaginary. So I'll be separating this real and imaginary part to understand the value to make this particular complex number in terms of a plus iv. So I'll be writing kp into 1 minus tau square omega square divided by 1 minus tau square omega square plus 2 zeta tau omega whole square. Uh, uh, just just wait 1 second. हेलो. हाँ मेघा. हाँ हाँ खुश रहो. Yeah. So again, I can write this over here. So this one is your imaginary part. So I can write minus 2 zeta tau omega divided by 1 minus tau square omega square and plus 2 zeta tau omega whole square into j. So this one will be your A, this one is your B. So that is equals to A minus IB form. So if I want to calculate mod of G of J omega, so that is equals to root over your A square plus B square. So that is equals to A square. So so finally you will see that is equals to your Kp square into 1 minus tau square omega square whole square, right? Divided by 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. Fine. Plus that is your B square. So again in B square, that here that will be also Kp, right? So that is Kp square into 2 zeta tau omega whole square divided by 1 minus tau square omega square plus 2 zeta tau omega whole square. And here in the denominator there will be also square. Here there will be also square and square. Right? I hope these things is clear. So finally, what I'll get that mod of g omega that is called as the amplitude ratio. Kp will come outside, right? And there will be a root. And finally, you will get this mathematical equation into the smaller one. So that is equals to 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. And that is your whole square plus 1 plus tau 4 omega 4 plus 2 tau square omega square plus 4 zeta square tau square omega square. Fine. I mean, definitely you will be getting some these kind of bulky mathematics. So you have to understand these things, right? Oh, sorry, this one is your negative, I think. Let me check which one is positive. This one is positive here, and this one is your negative. Okay. So this one is your negative here. This one is your negative and this one is your positive. Now, let's say your zeta is equals to 1. This is your critically damped system. So, I'll substituting zeta is equals to 1. Then what will we get? That your amplitude ratio that is equals to your Kp. And finally, if I'll substitute zeta is equals to 1, so what you will see that 1 plus tau square omega square minus 2 tau square omega square. Sorry, this one is tau 4 omega 4 and plus 4 tau square omega square. And this one is divided by 1 minus tau square omega square whole square plus 2 zeta tau omega whole square and divided by this one is whole square. Fine. So that is Kp. Finally, you'll see minus plus. So this will be plus. So can I write 1 plus tau square omega square? This one is whole square divided by 1 minus tau square omega square whole square plus 2 zeta. Again, this one is 2 zeta tau omega square. So I can write 4 tau square, 4 tau omega whole square, right? And there is a root and this one is your whole square. Fine. So finally, you will see that there will be a root and once we do the calculation over here, right? Once we do the calculation over here, it will come outside and finally you will see you will be getting Kp divided by root over 1 minus tau square omega square whole square plus 2 uh, tau omega whole square kind of thing, right? So this one is your amplitude ratio for the second order process, right? So directly you don't have to do that much derivation. I'm telling you one of the easiest way. How can I do? So you can do, let's say GS is equals to, let's say KP divided by tau square S square plus 2 zeta tau S plus 1. If this is your transfer function, if they are asking calculate GS, that is equals to amplitude ratio, you'll have to directly substitute Kp divided by root over, right? 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. I don't know what is happening here. That you have to remember this here for the second order process. Second order process, if you want to do derivation, it's very good. But if you don't want to do the derivation, you can remember these things very easily. I'm just telling you the method of how can you remember. Z of j omega. That is your Kp, and 1 upon 1 minus tau square omega square plus 2 zeta tau omega whole square. And zeta value can be greater than 1, zeta can be equals to 1, zeta can be less than 1, and zeta can be equals to 0. All these things I have told you in the previous lecture. What is the significance of telling zeta is greater than 1, equals to 1, less than 1, and equals to 0. All these things, right? Do you have any doubt now? So if you don't have any doubt, then please try to solve this particular thing. And again, the value of phi. Phi is equals to, again, tan inverse here. The value here, you have got the value of A and B, right? This one was your A and this one was your B. So B by A. So once you divide this particular thing, so you will be getting tan inverse minus 2 zeta tau omega divided by 1 minus omega square tau square. Right? So this is the thing. Only these two things you have to remember, and you can remember this very easily. Without, if you don't want to do all these kind of derivation, then it will be very. So again, the value of zeta, all these things you can go through that recorded lecture. You will get the recorded lecture there, because this value is again for the. If we talk about the value of zeta, zeta is greater than 1. I have told you that is called as over damped system. Zeta is equals to 1, that is critically damped. Zeta is less than 1, that is called as the under damped. And zeta is equals to 0, I have told you that is undamped system. So all these systems were there, and I have discussed all these things in that lecture. If you want to study more and more deeper in that about all these characteristics value of zeta, you can go through that particular lecture, and you can understand from there only, right? So, if I'll be discussing the value of zeta and all kind of thing right now, so again, I'll be very late, right? So please, I'll recommend you to go through that lecture right away just after the class, and you'll get to know why we are using calling zeta is greater than 1 and all these things, and what's the difference between the value of zeta over there, right? So now just try to solve one problem. Let's say your GS is equals to 3 upon 4s square plus 16s plus 4. Calculate the value of amplitude ratio and calculate the value of phi. This is second order transfer function, right? You just have to understand that these things is amplitude ratio, these things is phi, and what is the value of tau, omega, and zeta. If I am telling you omega is equals to 0.1, here, if omega is equals to 0.1, calculate the value of tau and zeta, phi and amplitude ratio. How many of you have solved? So let's try to understand how we can solve this kind of problem. So again, if I say you, so what is your second order transfer function? GS is equals to what? Kp upon tau s square plus 2 zeta tau s plus 1. This is your standard second order transfer function. And if any kind of problem is given, you have to convert this into this form. So this one is given 3 upon. So here you can see there is a 4, but here it is 1. So you have to convert this 4 into 1. So how can you convert this one? So can I write here this one is 3 divided by 4. I'll divide by 4 in numerator and denominator. I'll be getting 4 upon 4s square plus 16 by 4s plus 1. So finally, you will be getting 3 divided by 4 plus s square plus 4s plus 1. Is it clear? Tell me, anyone has any doubt? So the value of Kp over here is, you have got 3 by 4. Tau value is 1. 2 multiplied with zeta multiplied with tau. 2 zeta tau, that is used to be equals to 4, right? Tau is 1. So your zeta is equals to 2. So if your zeta is 2, then this is your overdamped system, right? You can understand this one. Now we have got all these value. We have got the value of tau. We have got the value of Kp. We know the value of zeta. We know the value of tau. We know the value of Kp. Can I calculate this amplitude ratio and that phi, right? So if I want to calculate the value of amplitude ratio, that is equals to Kp divided by root 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. So the value of Kp is 3 by 4 root divided by root over 1 minus the value of your tau. Tau is 1 and the value of omega is 0.1. Fine. So whole square plus 2 zeta. Zeta is 2, tau is 1 and omega is 0.1 whole square. So this one is your 0. So that is 3 by 4, right? Divided by 1, so 4 square. So this will be equals to your 4. That is equals to 3 by 16. So you have got the value of amplitude ratio that is equals to 3 by 16. Now you want to calculate the value of phi. Phi is equals to tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square. Am I right? Tan inverse minus 2 zeta tau omega upon 1 minus tau square omega square. So can I write tan inverse minus 2 zeta is 2 tau is 1 omega is 0.1 divided by 1 minus 0.1 whole square into 1 whole square. Is it clear? Or directly you can write in this way. That is 0.1 multiplied with 1 whole square. So this will be 1, 1 minus 1, 0. So can I say tan inverse minus infinity? So tan inverse minus infinity is equals to minus pi by 2. Fine. Is there any doubt in this particular problem? Tell me. What's the Alina? Is any doubt? Are you here?
Sir, how do we get minus pi by 4 for 5? Pi by 2?
Minus tan inverse minus infinity. What is the value of tan inverse minus infinity?
See, when we do 1 minus 0.1 into 1 plus whole square, 1 minus 0.1 square, that's what we get, right?
Okay, sorry. This one is 1. Okay. So sorry, 0.1, right? Good observation. So you will get the value, right? This one. That is your tan inverse minus 4 divided by 1 minus 0.01, right? So how much you are getting here?
Minus 22 degrees.
Minus 22 degree. Good, Alina.
And also for the amplitude ratio,
Yeah, so again, amplitude ratio, I think I have done some mistake over here. So that is 0.1 into 1. So that is 0.4 whole square, right? And that is 0.1, 1 minus 0.1. So could
yes,
you please do the calculation and
yeah,
tell me the correct answer?
get 0.702.
You are getting 0.072. So here you can, I mean, I was thinking this one is 10, but no, it's 1. No? So you will be getting 0.072, right?
So 0.702.
0.702. Okay, good. So you do the calculation correctly and after that you'll get it. But the method is same, right? So you have to remember these two things and maximum, if they are giving some second order kind of the question, then they won't do any variation. They will only ask you for the calculation and correct calculation, right? So yeah, this was the case. And the third one that I'm going to discuss about the transportation lag. This is very important concept, right? So what is transportation lag? So in PFR, I have taught this particular thing also, right? So if let's say you are injecting a red color over here, what will happen if the length is L? So once this red color cover this particular length L, then you will see the color in the outlet, right? So what is happening after a particular time, once it will cover this L distance, let's say it is traveling with the velocity v. So what will be the time to cover this L distance? So time is equals to L divided by v. So after this time, this red color will appear over here. So I mean, if at t is equals to 0, you are injecting over here. So after t is equals to L by v, you will see a color over here. So the output is getting delayed, delayed by a time tau. So that's why this is called as the transportation lag, right? So in transportation lag, you will see there is some different kind of uh, expression that will come. So here we are talking about the frequency response, right? So here, if I am telling your xt is there, right? If here your xt is your input, right? Now I am giving a xt input over here, and I want to know the output. So what will be the output if it is transportation lag? This one will be your output. So your output will be delayed by a time tau, right? And that time tau d, and that is called as the delay time, right? So your output yt that is equals to x t minus tau d, where tau d is called as the time delay. Sorry, td is called as, or tau d you can write. Tau d is called as the, means after insertion of xt at t equals t, you will get xt minus tau d, that is as your output y. Fine. So here your input is x is equals to your a sine omega t. This is your input. So what will be your output? Y. Y is equals to a sine omega t minus tau. Are you getting it? Only you have to replace t minus tau. That is what. And all these things will be same. The input you are giving here, that will be the same output we will be getting here, but we after a time tau d. Are you getting? After a time tau d, right? So this one is your yt. So this one is your yt. Yt is equals to a sine omega omega t minus tau d. So I want to convert this into ys domain. So what will happen? Your ys that is equals to, this one is your yt, right? So I want to convert into this one a sine omega t minus tau. So how can, I mean, again, this will become very complicated if you want to, convert S domain into this particular domain. So I'm directly writing you. I hope this you have understood. So the transfer function of transportation lag that used to be like that ys divided by xs, that is equals to e to the power minus tau s. And this is your tau ds, sorry. That is your time delay. That is minus tau ds, right? This is very important. Only you need to understand these things. E to the power minus tau ds. So this is your GS. You have got GS is equals to e to the power minus tau ds. This is your transfer function, right? Now, once you got the transfer function, the main aim is to calculate the amplitude ratio and phi. So I have told you that if you have GS, that is equals to e to the power minus tau ds, I'll substitute S is equals to j omega. So I'll be writing g of j omega, that is equals to e to the power minus tau d into j omega. Is it clear? So can I write e to the power I theta is equals to cos theta plus I sin theta? So can I write e to the power minus tau d omega into j, that is equals to cos tau d omega minus I sin tau d omega? Is it clear? So I'll be writing here that cos tau d omega minus I sin tau d omega. So this one is your A, this one is your B. So can I write mod of g of j omega, that is called as the amplitude ratio, that is equals to what? Root over A square plus B square to cos square tau d omega plus sin square tau d omega. And cos square theta plus sin square theta used to be 1. So the amplitude ratio for the time delay process will be always equals to 1. The amplitude ratio for the time delay process will always be equals to 1. Now, I want to calculate the value of phi. Phi is equals to what? Tan inverse B by A. So B is sin tau d omega, sin tau d omega divided by cos tau d omega. But this one is a minus. So can I write tan inverse uh, 10 minus tau d omega. So tan inverse 10 will get cancelled out. So that will equals to minus tau d omega, right? So the value of phi you have got, that is minus tau d omega. And this phi is in radian. Now, if we want to convert this phi in degree, so you have to multiply it minus tau d omega multiplied with 180 degree by pi. So now this will get converted into degree, right? So this is the way that you can convert this radians into degree and you can understand the value of transportation lag function. Anyone has any doubt? So if you don't have any doubt, then try to solve one problem. Let's say if GS is equals to e to the power minus 4s. So calculate the value of amplitude ratio and calculate the value of phi. If omega is equals to 0.25 radian per second. Have you got it? Alina, how much are you getting? How much? What is the value of phi?
Minus 57.3
So good. So definitely, whenever we talk about the amplitude ratio, so it will be one. For this is a pure time delay. And when we talk about this phi, so phi is equals to what I told you minus tau d into omega into 180 degree by pi. So tau d is minus 4, sorry, 4 tau d into omega. Omega is your 0.25 into 180 degree by pi. So this is 1, right? So that is equals to minus 180 degree by 5. So minus 180 by 3.14. So I think it will be less than 60 degree. I mean, it will be in between 55 to 60 degree, right? Okay, so I hope there is no any doubt. Then we'll move forward towards next topic, that is first order plus time delay. So first order plus time delay process, that is first order will be there, that is Kp upon tau s plus 1 and multiplied with time delay, that is minus tau ds, right? So this is first order plus time delay process. So if I want to calculate g of j omega, so what will be the value? I'll be substituting s is equals to j omega. So again, I'll be getting Kp upon tau j omega plus 1 multiplied with e to the power minus tau d j omega. Fine. So our aim is to calculate g of j omega, right? So directly, whenever you talk about this particular thing, where I have told you if I want to calculate z of two complex number z1 plus z2, z is equals to z1 plus z2, then I can calculate mod of z is equals to mod of z1 plus mod of z2, and phi is equals to phi 1 plus phi 2. So this one, I'll get a complex number in this form. This one is second complex number. So I can assume that one is Z1. That one is Z2. Fine. So we know the amplitude ratio of this one, that is equals to Kp upon root over 1 plus tau square omega square. And amplitude ratio of this one is equals to 1. So finally you will be getting that Kp upon root over 1 plus tau square omega square. Fine. Now if I want to calculate phi, so phi is equals to phi 1 plus phi 2. The phi 1 value over here is for first order tan inverse minus tau omega. And phi 2 value over here is minus 180 degree by pi into tau d multiplied with omega. So you will be getting the value of phi. So now I will be using the properties of the complex number, and after that I will be talking about this particular thing. So this was the amplitude ratio of first order plus time delay, and this one is the phase angle of first order plus time delay process. Is it clear? So this was the first order plus time delay. When we talk about second order plus time delay process, so the transfer function will look like this way: Kp upon root over tau s square plus 2 zeta tau omega plus 1 multiplied with e to the power minus tau d s. So again, this one is complex number, this one is complex number in the form. So again, if I want to write g of j omega, so I can write that is your amplitude, that is equals to amplitude ratio of this one, that is equals to what? Kp upon what? Root over 1 plus 1 minus tau square omega square. This was there, right? What was the value? Sorry, 1, I can write appropriately here. So that is 1 minus tau square omega square whole square plus your 2 zeta tau omega whole square. Fine. This was the case. And multiplied with the amplitude ratio of this one is 1. And the angle phi, that is equals to what? Tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square minus 180 degree divided by pi into tau d omega, where tau d only value is this magnitude we have to substitute. Already we are taking, here is negative sign, here is negative sign, right? This negative sign take care of this negative. Only the magnitude, let's say 4 is here, you just substitute 4. 5 is here, substitute 5. So this one is your time first order, second order plus time delay process, and all these are the amplitude and the phase angle of this particular process. So I hope there is no doubt. This is just a basic thing that I am doing here right now. This is just a complex thing. I mean, if you are very much comfortable in doing the calculation for the complex number, then these things will be very easy for you. So, if you are facing any doubt, you please go and study some basics of the complex number. Definitely, you'll get to know. And already I have discussed this complex number function right now in this particular lecture with you, right? So now, since we are studying here about the frequency response, and frequency response tells that, okay, if there is a transfer function of any first order process, second order process, or any time delay process, I'll be giving a sinusoidal input, and I'll be calculating the amplitude ratio and the phase angle phi. And this is very important to understand the frequency response of a particular process. Later on, I'll be telling about the stability, how we can understand whether the system is stable or not with the help of this frequency response. Till now, we have studied only the stability of the open loop transfer function, but frequency response, we can also analyze whether the open loop transfer function is stable or not. Will be telling about that thing, right? So before that, I'll be talking about some graphical representation of the frequency response, and that graphical representation is called as the Bode diagram. So what does Bode diagram tells us? So, I mean, in the simple term, if you want to define the Bode diagram, so this is a convenient graphical representation, of the dependency of frequency that largely eliminates the direct calculation, right? So when we talk about the Bode diagram, since here you see there is omega term, and omega is called as 2 pi and multiplied with f, where f is frequency. So omega is called as in radian per second, and the unit of frequency is equals to second inverse, right? So finally, 2 pi is constant. So omega is a function of frequency. So if I'll change the frequency, omega will get changed. So the thing is that if our first order transfer function is there, tau, let's say gs, that is equals to kp upon tau s plus 1. So if I'll change omega, how this value of gs, that is amplitude ratio, and phi is getting changed, right? So this is a graphical representation. There is a graphical representation that will give the relation of amplitude ratio and phi with respect to omega, right? And that the graphical representation is called as your Bode diagram, right? So in Bode diagram, generally, what I do, Bode diagram is just a relation of log of amplitude ratio versus log of omega. That's it. If we are able to plot, sorry, log of omega naught, that is omega tau. Log of amplitude ratio versus log of omega tau, right? Or if phi versus omega tau. So this is called as the Bode diagram or Bode plot. Both frequency, log of amplitude versus omega tau, and log of phi versus omega tau, right? So we can analyze these things over here. Now, what? Now, how we will plot this Bode diagram? That's very important, right? So then move forward. What the first order process? First, I'll talking about first order. What was our first order process? Gs is equals to what? Kp upon tau s plus 1. And what was the amplitude of this one? That was your Kp upon root over 1 plus tau s square omega square. And the value of phi was equals to your tan inverse minus tau omega. So our aim is to, let's say, tau omega and log of your amplitude ratio. So if this one is amplitude ratio, so if I'll do the calculation of the amplitude ratio over here, so if I want to find out log of amplitude ratio, that is equals to what? Log of Kp minus 1 upon 2 log of 1 plus tau square omega square. Is it clear? Tell me. Now, let's try to understand if omega is equals to 0. So what will happen? If omega is equals to 0, log 1 0. So log of amplitude ratio, that is equals to 1. What? Log of Kp. Now, omega tending to infinity. If omega tending to infinity, what will happen? Log infinity minus infinity, right? And something minus infinity. What will happen? Log of amplitude ratio should tending to 0. Something minus infinity, that is equals to 0. That's it. Fine. And let's say omega is equals to 1 upon tau, right? And this is called as the cross, when omega is equals to tau, that is called as the corner frequency. And this is denoted by omega c. So if omega is equals to tau, then it is denoted by omega is equals to omega c, that is equals to 1 by tau. So that is log of amplitude ratio. What will be the value? If omega tau is equals to 1, right? Omega is equals to tau. So what will happen? Omega tau is equals to 1, right? So log of 2, log of Kp minus 1 upon 2, log of 2, right? So there is a finite things over here, right? So at omega is equals to 0, you are getting log of amplitude ratio is equals to log of Kp. So this will be equals to here, log of Kp, right? So it will go like that. and it will go like that. So at this point, what will happen? At this point, you see there is change in slope over here. Here there is omega tending to 0. Till now, omega is equals to 1 upon tau. That is omega c. The slope will be 0 here, right? Here you see, for if omega is 0 or omega tending to 0, means here omega is 0. Between omega 0 to omega 1 by tau c, slope will be 0. And after that here, slope will be equals to -1. This is for the first order process, right? And when omega tending to infinity, you see this value will be going to 0, right? Omega tending to infinity, this value will be 0. So the thing is that you need to understand, in case of first order process, this point is called as the point at which the slope is getting changed, and it should be going like that, but slope is getting changed here at corner frequency, and that omega c is called as the corner frequency. And before corner frequency to omega is equals to 0, the slope will be equals to 0, and the value of log of amplitude ratio, that is equals to log of what? Kp, right? Log of Kp. Is it clear? So two terms are there. Here this is called as law frequency asymptotes. And since omega is very, very greater than 1, very, very high, so this is called as the high frequency asymptote. This is called as the high frequency asymptote. Anyone has any doubt? So this one is the body diagram of first order process. Is it clear? Okay. So let's say, if let's say gs is equals to, let's say 1 upon 2s plus 1. So how can I draw the body diagram of this particular thing? So since we know this one is a first order transfer function, right? Tau is your 2. So your crossover frequency omega c is equals to what? 1 upon 2. That is equals to 0.5. So the thing is that, so if I want to draw log of amplitude ratio versus tau omega, so initially the slope will be 0. At omega is equals to 0.5, the slope will be equals to -1, right? So here you will see slope is equals to -1, and here slope is equals to 0. Is it clear? either you can plot this in log of amplitude ratio, or you can also plot in terms of amplitude ratio only, right? In terms of amplitude ratio and in terms of omega tau, right? So if you are drawing in log of amplitude ratio, the precision will be very high. Your graph, your plot will be looking very, very fine. You can calculate value at any point of time or any particular time, right? But if you are trying to draw by amplitude ratio versus omega tau, so graph will be looking like a kind of bulky kind of thing, right? But yes, this one is also body diagram. This one is also body diagram. Again, it will be also, the shape will be also looking like that. Here, omega is equals to 1 upon tau, and that is equals to omega c, that is called as the corner frequency. Is it clear? Okay, so if you don't have any doubt, we'll take 10 minutes break, and after that we'll again join. Again we'll come and we'll complete the body diagram and body stability criteria at least today. This is only 30-40 minutes type topics that has been left right now. I'll complete this today by itself. And again, tomorrow I'll be talking about all these stability of the control loop, open loop transfer function, closed loop transfer function, and Cohen-Kuhn method, Ziegler-Nicholas controller tuning and all. And after uh, that, I'll move forward towards the feedback control and the cascade control system, right? Tomorrow. But today I'll be completing about all these stability criteria for the with the help of body stability, right? So within 10 minutes, again come. So, hi everyone, am I audible? Okay, so till now we have studied about the Bode diagram for first order process. Now we'll move forward towards the second order process. Again, this is very important. So the second order process looks like this one: Kp upon tau s square plus 2 zeta tau s plus 1. And the amplitude ratio for second order process, that is equals to Kp divided by root over 1 minus tau square omega square whole square plus 2 zeta tau omega whole square, right? And the phase angle phi is equals to tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square. If you remember this one, then you have to divide this by this, that is equals to your phase angle phi. That's it. So if you remember the amplitude ratio, the phase angle itself will get remembered, right? So now, so let's say I want to plot amplitude ratio versus omega, amplitude ratio versus tau omega, right? So the thing is that if let's say omega is very less than 1, omega tending to 0, what happens at amplitude ratio omega tending to 0? So this will be 0, this will be 0. So that will be equal to amplitude ratio will be Kp. So this will start from Kp. Let's say omega tending to infinity. What happens? If omega tending to infinity, this will be infinity, this will be infinity. So your amplitude ratio will tending to 0. Let's say omega is equals to 1 upon tau. So what will happen? And that is called as omega c. So if this is 1 by tau, so this one will be 0. So this one will be omega is equals to 1 upon tau. So 1 upon 4 zeta square, right? So your amplitude ratio, that is equals to Kp divided by your 4 zeta square. So this will depends upon zeta. So if I'll increase zeta, amplitude ratio will decrease. If I'll decrease zeta, amplitude ratio will get increase. So this is the case of the zeta, right? So here your amplitude ratio depends upon two things, that is zeta as well as Kp. So it will start from here. Initially slope will be 0 and it will go like that. But here slope will be minus 2, right? Here slope will be minus 2. But here you see, it will also depends upon zeta. If I'll increase zeta, amplitude ratio will decrease, right? With respect to your omega. So here you will see these kind of things will be there. All these things will start from same point. So if I'll go from here to here, what will happen? Your zeta is decreasing. This will be the plot that will look like in terms of zeta. Here zeta will be equals to 1. Here zeta will be equals to 0.8. Zeta will be equals to 0.6. Zeta will be equals to 0.2. Like that. Here if I'll go from this side to this side, zeta will be decreasing. So this is the, and here slope after this particular point, here omega c is equals to 1 by tau. That is called as the corner frequency. Your slope will be minus 2 and here slope will be equals to 0. That is the thing that you need to remember. Fine. Now, next is coming to phi. Your value of phi for second order process, that is tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square, right? So how we are calculating this one? Let's say omega tending to 0. If omega tending to 0, so this will be 0. Your phi will be equals to tan inverse minus omega tending to 0, that is equals to 0, right? So if omega is 0, right? So what will happen? Your phi is 0. Now, let's say omega tending to infinity. So what will be the phi? If omega tending to infinity, so what can I do? That this will be infinity divided by 1 minus infinity square. Or I can do these things. Tan inverse, I'll divide numerator and denominator by omega square, right? So that is equals to minus 2 zeta tau omega divided by omega square divided by 1 by omega square minus tau square, right? So omega tending to infinity, this will be 0. This will be your 0. But here minus 0 is 0. But here that is equals to what? This will be 0. 0 by something. Are you getting it? Omega by omega square. So omega and omega will get cancelled out. So minus 2 zeta tau by omega square. Omega. So again it will be 0. 1 upon tau omega square. It will be 0. And this is minus. So when omega tending to infinity, so the value is equals to 180 degree. It used to be minus 180 degree. Because at the same time it cannot come. And when omega is equals to 1 upon tau. So your phi is equals to what? Omega is equals to 1 upon tau. So this is 1 minus 2 zeta divided by 1 minus 1, 0. So that is equals to phi is equals to minus pi by 2. So you see here at omega is equals to 0, it is 0, again minus 180 degree and it is minus pi. So how can you plot this particular curve? So this curve will look like this one. Let's try to understand. Let's say this one is your phi angle and this one is your omega tau angle axis. So here let's say phi is 0, phi is your minus 90, and here let's say phi is your 180 degree, right? So at omega tending to 0, what here this one is your omega is equals to 0. Omega is 0, this one is 0. It will go to minus 90 and it will again go to this kind of thing. So this will look like this one. Asymptotically, this will go like that. And again, this will go like that, right? And the point at which your phi is minus 90 degree, that is called as omega is equals to 1 upon tau. And that is equals to omega c. Is it clear? Anyone has any doubt? This will look like that. So, but again, if I am drawing in this way, next one is that if I want to draw some like that, and all this will start from here only, right? So if I'll go from here to here, what will happen? Zeta is decreasing. If I go from here to here, zeta is decreasing. Are you getting it? Here to here. So this is the case of second order process. So second order process, this is the value of phi, this is value of omega tau, and the curve will be like that. Anyone has any doubt? Okay, so this is second order process. One kind of second order process can be, let's say your GS is equals to, let's say Kp upon 2s plus 1 and let's say 3s plus 1. So what will happen? First, you have to find out crossover frequency. So omega C1 is equals to what? 1 upon 2. And omega C2 is equals to what? 1 upon 3. So that is equals to 0.5. That is equals to 0.33. So this one is less. So this is second order process, right? So let's say omega tau. This one is your amplitude ratio, right? And this will start from Kp, right? Now, at omega tau is equals to 0.233. So here 0.33, and what that is that 0.5. Sorry. Here tau omega is equals to 2, and here tau omega is equals to 3. And here crossover frequency is equals to 1 by 2, and here crossover frequency is equals to 1 by 3. Right? So right now I am drawing with respect to omega tau. So you can draw with respect to this one or only with respect to omega as well, right? So let's say it will start from here. It will go up to here with a slope of 0. After that, it will come here after a slope of -1, and again it will turn here at this particular point and at this particular point, and here you will see slope is equals to -2. Are you getting it? So you have to do this kind of thing. You have to make the Bode plot in this way. First, up to your omega tau is equals to 2, which is less, it will be slope will be 0. From 2 to 3, you see there are two crossover frequency having omega tau 2, omega 3, tau 3. So in between, the slope will be 1. And finally, since this is second order process, so the slope will be -2. Either you can plot this curve in terms of omega tau, or you can draw only with respect to omega or amplitude ratio, right? So if omega is there, so omega C1 is less than 0.5, and here it is 0.33. It is 0.33. This is 0.5, and this will start from Kp. First, it will come up to this particular point with a zero slope. Slope is equals to 0. Again, it will turn here. Here, slope is equals to -1. And again, the slope will be like that. And here, at this particular point, it will again turn. And here, slope will be equals to -2. Is it clear? So you don't have to actually draw all this plot in the examination. Only you have to analyze how I can know the nature of the curve. Why is here 0.33, why here it is 0.5, or if I'm drawing in terms of omega tau, why here it is 2, why here it is 3, why slope is 0 here, -1 here, -2 here. You have to understand this way, right? So let's say one transfer function is given, let's say 3 upon 2s plus 1, 4s plus 1, and s plus 1. Now you have to draw the Bode diagram over here. So the amplitude ratio, since this one is your Kp, this is your third order process. So this one is your amplitude ratio, and this one is your omega. I'm drawing with respect to omega. So here you see omega tau plus 1. So omega C1 is equals to 1 by 2. Omega C2 is equals to 1 by 4. And omega C3 is equals to 1 by 1. So that is equals to 0.5, 0.25, 1. So we are having 0.25, 0.5, 1. So initially what happens, this will start from 3 because our Kp is 3. Till first frequency, it will go to a 0 slope. Till first to second frequency, it will go to a -1 slope. This till second to third frequency, again, it will go to some this particular slope. And again, from this particular onward, again, this will go like that. So here, what you see is, here your slope will be equals to 0. Here your slope will be equals to -1. Here slope will be equals to -2. And here in this region, slope will be equals to -3. So this is the way that you can understand how this Bode diagram look like in different region for a different processes. Is it clear? So subsequently, you will see if all the transfer function are in the denominator, then slope will be looking like this. In frequently, in 0 to this particular region, there will be 0 slope. Again 1. You'll have to add one more slope in every subsequent frequency region, right? Now, this was the process. Let's say Bode plot for P controller, proportional controller. So the transfer function of proportional controller is just a C, Kc. So the amplitude ratio will be equals to what? Kc. And phi is equals to what? Tan inverse B by A. B is your imaginary part, A is your real. So here only you see in transfer function, only real part is A, B is 0. So your transfer function is your phi is your 0 degree, right? So the transfer function of proportional controller will look like this one. If I am talking about omega, if I am talking about amplitude ratio, this will be like that. And this is your Kc. Anyone has any doubt? And what about phi? If this is omega, this one is your phi, and let's say this phi is equals to 0 degree. Now this one is your P controller, proportional controller. Now, if I move forward towards the second one, that is PI controller. The transfer function of PI controller was what? Kc into 1 plus 1 upon tau is. Is it clear? So can I write Kc into tau is plus 1 divided by tau is? Or we can write Gc is equals to Kc plus Kc upon tau I into 1 upon f. If I will substitute g of j omega, so can I write Kc plus Kc upon tau I 1 upon j omega. So finally, can I write Kc is equals to g j omega is equal to Kc plus Kc by tau I into 1 upon j omega into j omega divided by j omega. Fine. So g of j omega, that is equals to Kc plus Kc upon tau I into that j omega square, that is minus, here it will be minus j square omega square minus into j omega divided by omega square. So omega and omega square will get cancel out. Your g of j omega, that is equals to Kc minus Kc divided by tau I omega into j. Fine. So your amplitude ratio, that is equals to what? This square plus this square. So Kc square plus Kc by tau I omega whole square root over. So this one is your amplitude ratio for proportional integral controller. Right? Now, if I want to calculate the value of phi, phi is equals to how much? Tan inverse this B divided by A. So that is Kc by tau I omega divided by Kc. So this will get cancelled out and it will be minus. The value of phi is equals to tan inverse minus 1 upon tau I omega. Is it fine? So we have got the amplitude ratio is equals to that Kc plus this one and the phase angle phi. This is called as the phase angle. I'm doing nothing. Nothing new is there. Only I'm repeating the same that I have done previously, right? Same thing I'm doing repeatedly. Now, want to draw a Bode diagram. So, Bode diagram consists of that amplitude ratio 1 plus 1 upon tau I omega square and phi that is equals to tan inverse minus 1 upon tau I omega. So, if I want to draw amplitude ratio versus omega, that amplitude ratio versus omega, fine. I think it was a Kc over here. So here it is Kc. So let's say if omega tending to 0, what will happen? Omega tending to 0, 1 upon 0, infinity. So your amplitude ratio tending to infinity. And if omega tending to infinity, your amplitude ratio will be 0. And if omega tending to tau I, omega tending to 1 upon tau I, what will happen? Your amplitude ratio is equal to this one is 1, so 1 plus 1, 2 root 2 into Kc, right? So this will be the case. So how will it look like? At omega tending to 0, it will be infinity. Amplitude ratio will be infinity. And at omega tending to infinity, amplitude ratio will be 0. And omega tending to something, omega tending to 1 upon tau I, right? So this will be equals to root 2 into Kc. So how will it look like? So So at omega tending to 0, it is going to infinity. So it will be like that, right? And again, it will go like that. So this will be a point where omega is equals to 1 upon tau I. Is it clear? No, when omega tending to 0, infinity, it will be equals to 1. This will become 0, so it will be 1. So this graph will look like this one only. Finally, it will come and becomes constant to value 1. And this is your 1. Right? So this is the plot of proportional integral controller that if this is coming like that and going like that, first decreasing, then becoming constant, this is your PI controller. Is it clear? Now coming to phi. If omega tending to 0, what will happen? Omega tending to 0, 1 by 0 minus infinity. So phi is equals to tan inverse minus infinity. So that is equals to minus pi by 2. When omega tending to infinity, what will happen? It will be 0. So phi is equals to tan inverse 0. So that is equals to 0. So what will happen? If I want to draw this one, that is equals to phi, that is your, this one is your phi, that is your omega, right? And when omega tending to 1 upon tau I, what will happen? Phi is equals to tan inverse minus 1, that is equals to minus pi by 4. That is minus pi by 4. So how will it look like? Minus pi by 4, 0 and minus pi by 2. Is it clear? So that is 0, that is minus pi by 4 I can assume, and that is minus pi by 2, right? So initially at omega tending to 0, it was minus pi by 2. So it will start from here. It starts from here, right? And at omega, this one is omega minus pi by 4. So don't you think? And at omega tending to infinity, it is 0. So something it will be coming like that. It is 0 and it is going like that. And something like that will be there. Right? And this is point where omega is phi is minus pi by 4. And at this particular point, omega is equals to 1 upon minus tau I. Right? So this will be the plot of this integral controller, proportional integral controller. Is it clear? Now, if it is clear, I'll move towards the next controller third, that proportional derivative. So the transfer function of controller will look like Kc into 1 plus tau ds, where tau d is your delay time, right? Derivative time constant. So if I want to calculate g of j omega, so can I write Kc into 1 plus tau d j omega. So again, you have to separate real part and imaginary part. Kc plus Kc tau d into omega into j. So this one is your A, this one is your B. So the amplitude ratio is mod of j omega, that is equals to root over k square plus Kc tau d omega whole square. Is it clear? That is Kc also. So Kc will come out and it will be equals to 1 plus tau d square omega square. And the value of phi is equals to tan inverse Kc tau d omega divided by Kc. So Kc and Kc will get cancel out. That will be equals to tan inverse tau d omega. So eventually we have got the value of both amplitude ratio as well as the phase angle. So the ultimate aim is to draw the body diagram for proportional derivative controller. So we have got the value of amplitude ratio, that is equals to your Kc root over 1 plus tau d square omega square. So let's say omega tending to 0. So your amplitude ratio, if it is 0, that amplitude ratio will be Kc. And when omega tending to infinity, amplitude ratio will tending to infinity. So it's very simple body plot of uh, proportional derivative controller. This one is your amplitude ratio, this one is your omega. And when omega is equals to 1 upon tau d, your amplitude ratio is equals to what? Kc multiplied with root 2. So again, this will go like that. I mean, something like that. This will go and again this will go. It will start from this Kc and at this particular point, this is equals to Kc root 2, where omega is equals to 1 upon tau d. And at omega tending to infinity, it will go to infinite value. Is it clear? Okay. So one more thing that has been left here is fourth one, that is Bode plot for time delay process, that your Gs is equals to e to the power minus tau ds. So here amplitude ratio was 1 and your phi is equals to minus tau d into omega into 180 degree by pi. So when we draw the amplitude ratio omega and amplitude ratio, so definitely this will be equals to 1. When comes to phi is here. So if omega is equals to 0, your phi is equals to 0. If omega is equals to infinity, your phi is equals to minus infinity. So This will be your phi, this will be omega, this it is 0 and it will be going like that, right? So only one a single process is there where your value of phi tending to infinity in case of time delay process or pure time delay process, right? Do you have any doubt? Darshan, are you getting it?
Yes, sir.
Okay. So this was pure time delay process. Now I will be clubbing both sum of, have you written it? Okay. So let's try to understand one more thing. Let's say if your transfer function is given like that, 2s plus 3 divided by s plus 1 into 4s plus 1. 2s plus 1 divided by 4s plus 1. Now, since first, in case of Bode diagram, what you need to understand is here this is tau s plus 1, tau s plus 1, tau s plus 1, right? First, you have to calculate omega c1, omega c2, omega c3. How we calculate omega? If this is tau s plus 1 kind of thing, so your omega c1 is equals to 1 upon tau, right? So let's say here omega c1 is equals to 1 upon 1 by 2. Sorry, 1 by 2. So here this will be 0.5. Here this will be 1. Here this will be 0.25. So three corner frequency we got. This is omega. This is your amplitude ratio. One corner frequency is at 0.25. One corner frequency is at 0.5 and one is at 1. Is it clear? Now, what I told you, since initially, if you see, the lowest corner frequency is 1 upon 4s plus 1, that is 0.25. So initially it will start from here something, right? It will go a 0 with a 0 slope. Once it will go to 0.25, so 0.25 to 2, 5, what you see? The slope is of this one, right? 2s plus 1. And this is integral kind of control system. So this will go like that. Is it clear? Fine. And beyond that, again, here this is slope is 0, slope equals to 1, and beyond 4s plus 1, let's say 2s plus 1, there is s plus 1. So slope here would be equals to, again, what? Minus 1. So finally, it will go like that only. Slope is equals to minus 1, right? Since in between 0 to 0.5 to 0.5, this integral controller will show the action because 0.25 is the corner frequency of this. And beyond that, this particular term will come dominant. And before this term will dominating over here. I think it should be like that. Again, I'll have to draw it. This one is your first order process. So for first order process, slope is negative. So it will go like that, minus 1 slope. Now the integral control action will come in the action for this. So it will go like that. No, no, no. Again, minus 1 slope and plus 1 slope. The slope will become 0 over here. So the slope will be 0 here, right, till now. And after that, this again transfer function which is in the bottom, it will show a negative 1 slope because for this slope is minus 1. For this slope is -1 and for this slope is +1, I told you. So again, here it is showing -1 slope. So here -1 slope, here slope is 0, here again slope is -1. It will look like that one. Again, in the next class, I'll be discussing some complicated example of Bode diagram. So till now, I think it's more than enough for today. All these things were there. Again, tomorrow I'll complete the frequency response and we'll start some advanced control strategy, that is cascade control and feed forward. That is very, very small topic and some stability criteria for this frequency response, right? That gain margin, phase margin, all these things I'll be discussing about today. So do you have any doubt for today's class? If you have any doubt, you can ask right now or you can leave. If you don't have any doubt, then you can leave.